Good morning, class, or afternoon, whenever you're waking up to this video. I want to do a quick rundown of what you're going to be doing today. I know we were expecting to have a test. I know you're so glad you're not going to have that today, but remember, you got to do it on Friday. So you might want to do a little bit of review for that. Just double check to make sure you've got your shapes and stuff down. You've got all the information I could give you, and now it's just a matter of you putting it into practice. So we're going to start off with looking at the module. If you get into Canvas, you'll see that I have Unit 9 now. I'm putting them at the top so you don't have to scroll so far. And there are 3 things that I want you to do today. The first thing is an appropriate snowflake video for a snow day. It's a TED Talk. It kind of summarizes what we have done, gives a quick introduction to some of the things that we're going to be doing, because we are going to be talking about what we call intermolecular forces, or attractions between molecules. So that polarity that we talked about in the last class, especially in determining whether a molecule is polar or not, is really important to that next step, because the polarity of a molecule is going to determine how well they can attract each other, and the strength of that polarity, the stronger it is, the stronger the attractions. Even nonpolar molecules will have attractions between each other, but that occurs through a special way. So the second thing I'm going to have you do here is I've got a link to a document titled Intermolecular Forces. It's one I put together, scrounged together to kind of summarize. So I know it's still textbooky, but it's not a textbook, and tries to get straight to the point with everything, with some diagrams and examples. It starts off with a flow chart of the different types of intermolecular forces. We call all intermolecular forces van der Waals forces, and then we subcategorize those from there. So quick rundown here: we got London dispersion forces, dipole-dipole forces, hydrogen bonding, which I'm sure some of you remember talking about in probably biology class, but that's a special version of a dipole-dipole force. We have what's called dipole-induced dipole forces, and then we have ion dipole forces. So read through that so you get definitions for those. But the most important thing is this worksheet that I'm going to have you work through, titled Intermolecular Forces Worksheet. It's linked to, everything's in Google Drive, but it's linked to from the Canvas site. When you go into open that up, please read the introduction, and you're going to have what they call critical thinking questions, basically questions to answer. Anytime you see the abbreviation CTQ, it's basically just saying answer question number 2. So if it says CTQ2, it's referring to question number 2. As you go through and read through this, the most important part of this document is this table that is on the second page. And I want to point out a couple of things because I'm not there with you guys. So if you look at, excuse me, if you look at the breakdown of this, there are 3 categories of compounds they are going to be referring to in the worksheet. Alkanes, which are compounds that only have carbons and hydrogens in them. Ketones, which are going to have carbons, hydrogens, and an oxygen, but the oxygen has a double bond to one of the carbon atoms. And then the third category is the alcohols, and that's going to have carbons and hydrogens and oxygen. The oxygen is going to be singly bonded to one of the carbons with a hydrogen coming off of the oxygen. Now, I'm going to show you a quick model kit that I found that works on the iPads, works on a laptop, and help to illustrate how you could use this possibly to help with the assignment. So I'm going to make one of each of the compounds. I'll help you interpret them and see how it's used with this. So if I wanted to make pentane, so pentane has this formula of CH3. I'm going to zoom in here. Oops. CH3, C2H2 in parentheses 3, and then CH3. Now how we would interpret this is that there are going to be 1, 2, 3, 4, 5 carbons all in a row, and then we will have hydrogens attached to those. The ones on the end will have 3 hydrogens attached to the carbons. The ones in the middle will have 2, and we'll see that here in just a second. So when you open up this modeler, and I have a link to it in Canvas below the page for today. So when you open it up, you're going to see this show up first. And I'm going to try to keep it as simple as possible. If you mess up, simply go down to Start a New Model. If you click on that, it'll just bring up another, what we call methane. So I need to add more carbons. I need to add a total of 5. So I'm going to click on the carbon, and it doesn't really highlight anything, but it changes the text here. And what I'm going to do is if I click on this hydrogen atom, that will replace that hydrogen with a carbon. And notice now we have 2 carbons, each one of them with 3 hydrogens on it. This is a little more complex modeler than the other one that we were working with. I just found this today on the 23rd, so still trying it out, but I think it'll work fine. So that gives us 2 carbons. We need 5, so I'm going to click another hydrogen to add 3 carbons. I'm going to click another hydrogen to add a 4th, and then I'm going to click another one to add a 5th. Now we can rotate this around, and you can see now that I have 5 carbons. And to see how that interpretation with the formula went, we have CH3, and then this carbon has CH2, this carbon is CH2, and this carbon is CH2. So if we go back and look at this, this is why they had this in parentheses, CH2 in parentheses with 3, because there are 3 of those. And then the last carbon is another CH3. Now the thing I like about this modeler here is that it also allows us to look at how the charge is distributed around the molecule. Now I've explained polarity and polar and nonpolar as if they have an area that's positive and negative on the outside. And if they don't, it's nonpolar. Now, we will see if you click on this button that says MEP, it has, I'm not sure what the technical name for that they're using here, but what it does is it puts around that molecule a cloud, and the color of the cloud is associated with the charge. And we can see what the color codes are down at the bottom here. And we can see that the green is associated with 0 charge. So as we rotate this around and look at it with that charge cloud around it, we can see that there's nothing that's different. All of the charge is 0 essentially on the outside. Now I'm going to clear this, start with a new model, and I'm going to go to, and let's do pentanone. So 2-pentanone is going to be similar to the pentane. Notice the 2 names start with pent. In the virtual modeler here, I'm going to add 5 carbons. So I'm going to click carbon. I'm going to add 5 carbons in a row, number 5. And then all of these molecules that are in the ketone section have the carbon on the, they have the oxygen on the 2nd carbon. So in my model, I'm going to change, and what you can do is I'm going to click on the oxygen. I'm going to change this hydrogen to an oxygen. Now the thing it does is it adds the oxygen, but it has a hydrogen on it. It's also got a single bond, and if we look at this document here, we need to have a double bond, or down here, pentanone. So over here, I'm going to click double, and I click on the bond for the oxygen, and it changes it to that double bond oxygen, removes the extra hydrogens, and makes the formula correct. So now I have 5 carbons in a row. I have my CH3. I have my carbon with the oxygen on it. I have 2 carbons with 2 hydrogens on it, and I have my CH3. And finally, if I hit this button that says MEP, we can see now how the polarity exists in this molecule. This area of red is associated with a negative value, and this area of blue is associated with a positive value. So the polarity of this molecule, it is polar, with the oxygen being negative and these areas, these hydrogens here, being positive. Notice though that these hydrogens on the end still are green with very little charge. And that's going to be a factor to take into consideration when you look at the larger molecules that occur, like here with this one, 2-decanone, which is actually going to have 10 different carbon atoms in a string. And you can make that with the modeler that I just showed you. The last group is these alcohols, and they are really simple to make because all you have to do is replace a hydrogen with the oxygen, and it will automatically place the hydrogen on it for you. So if I'm going to stick with the pentanes, I'm going to do 1 pentanol, so I'm going to put 5 carbons in a row, and what this interpretation at the end here is, this oxygen will go on the last carbon, and you'll see how that looks. So I'm going to make 5 carbons in a row, and then one of these hydrogens I'm simply going to replace with an oxygen, and notice that it puts the hydrogen on that with it. So that's all you'd have to do for the alcohols, is on the end simply replace one of the hydrogens with oxygen. And again, I'm going to show the MEP, which is going to show that charge distribution. And we can see that in this molecule here, the polarity is focused up here, with one area around the oxygen being negative and the area around the hydrogen that's attached to it being blue. And these areas a little bit blue here, but again, we have this area at the opposite end that doesn't have much charge associated with it at all. So answer those questions based on these compounds, and you're going to be looking for patterns. You're looking at the weights. So this is the mass off the periodic table. These are your boiling points. And the questions are going to be asking you to make some analysis of what the patterns are, what reasons possibly are there for those, and making some comparisons about the polarity of the molecules. I want you to answer 1 through 17 as best you can. If you can't answer a question, then you better have a question ready to ask about why that you cannot do that. So do those as best you can. Have those ready to go for Friday after we take the test. The test is going to be 9 questions that you're going to have to do the Lewis structures for. So it's not going to take the entire period, and whatever is left, we will cover this and help review to make sure that we're caught up.